Hello and welcome to today's webcast, brought to you by Cabling Installation and Maintenance. Today's event, titled Minimizing Deployment Costs of Enterprise Fiber, will be presented by Robert Reed, Senior Product Development Manager with Panduit Network Connectivity Group, and by Harley Lang, Director of Marketing with Fluke Networks. The event is being sponsored by Panduit and Fluke Networks. Our thanks go to these organizations for sponsoring today's webcast and for presenting the information that you'll see and hear today. My name is Patrick McLaughlin with Cabling Installation and Maintenance, and I will moderate today's webcast. The presentations that you'll see today address some very practical means of deploying and testing fiber optic cabling systems in enterprise as well as data center environments. First, Robert Reed will provide information on network data rates and the fiber optic systems available to support those data rates. That information will be the backdrop for what Robert will explain about how fiber systems can meet appropriate power and loss budgets, including field termination options that are available for fiber optic systems. He will also discuss some certification and troubleshooting issues. Then Harley Lang will provide detailed information about the importance of testing fiber optic systems of all types and all termination styles. His presentation will include step-by-step measures for certification. It also will explain how to eliminate guesswork during certification and some remediation efforts that can be made. Following the presentations, we'll have a question and answer session. You can ask questions at any time during the presentation via the web using the question window that you see on your screen. We recommend that you close other applications on your computer for best performance of this webcast. Also, this presentation will be available on demand within 24 hours of the conclusion of this event today. Excuse me. Also, to the members of our audience, this seminar qualifies attendees to receive one continuing education credit for the following BICSI designations: RCDD, Installer, Technician, RITP, and Certified Trainer. Please know that at the conclusion of the event, you will see a pop-up window that tells you that you are eligible for a certificate of attendance. A link to that certificate of attendance will then be emailed to you at the email address that you provided when you registered for today's event. So again, that's a little different from what we've done in the past. There will not be a certificate itself that pops up, but rather a notification that pops up, and then you will receive an email with a link to the certificate. So with that housekeeping out of the way, it gives me great pleasure to introduce today's first speaker, Robert Reed. Robert, whenever you're ready.
Thanks for the intro, Patrick. Without further ado, I'm going to step right into the agenda for today. We're specifically going to talk about enterprise backbones and probably less about data centers and some of the issues surrounding commissioning of links, uncertainty with respect to testing in the field, uncertainty with respect to which connector end to remediate and so forth. We're going to go through some of the cabling applications and standards for what Panduit calls high-speed data transport. We'll go through some of the installation practices, specifically with respect to Tier 1 testing and some of the uncertainties that arise from that. The centerpiece of the presentation is really a cost model that we've developed that shows the value of reterminable connectors and really the value of Tier 2 testing, which leads into the second presentation. And without further ado, we'll go to the second slide. So this is a snapshot of the high-speed cabling market. In enterprise networks, we're just seeing a nascent market with respect to 10 gig backbones, and we'll talk a little bit about that in the context of a standards discussion. So for most backbones in the enterprise today, 1 gig Ethernet is the norm, and backbones typically are fiber, and we'll talk about multi-mode fiber in particular in the context of the standards. Not talking about 40 and 100 gig, and if you overlay that forecast on top of this, you're seeing, these are hundreds of millions of ports. 40 and 100G is probably 1,000th of that number, so we won't talk about that. Directly out of the IEEE standard, the focus of the discussion will be on multi-mode fiber, of course. But here we have a 10 gig channel with OM3 fiber. We've got some things kind of grayed out here that you really can't see in the graphic, but you can see that the total power budget for an OM3 channel, 300 meter channel, is 7.3 dB. The things that a contractor can affect are highlighted in red there. Channel insertion loss, in particular the connectors and the fiber that are in the channel. The ISI, we won't talk too much about that, but that's related to the bandwidth of the fiber, and you can make some trade-offs of power penalties associated with ISI by shortening up the channel or by using a higher grade fiber like OM4, and you can trade that off with connectivity. I wanted to focus on this a bit. These are snippets right out of the 10G base SR, the 10G standard, IEEE 802.3 AE. These are paragraphs within the standard that talk to the component expectations in the field as tested. So you can see there that that last slide, I'm just going to head back one slide a bit here. So channel insertion loss, 2.6 dB. So we've got 1.5 dB of connectors and 1.1 dB of fiber. With respect to the standard, that 1.5 dB of connectors, it really comes from two 0.75 dB connectors. So that's the paragraph out of the standard, and this is an expectation on component loss, individual component loss in a channel, in a backbone. So not only do you have to have 1.5 dB max of connector loss, there's an expectation on the components in the 10 gig standard that says no more than 0.75 dB per connector. The next paragraph down is discrete reflectance, and this is something that typically isn't measured in the field with Tier 1 testing, power testing, but it is something that you could potentially measure with Tier 2 testing, OTDR testing. And what this says is that the maximum discrete reflectance or return loss for the channel, so that's on a component basis, each connector shall have no less than 20 dB return loss or no greater than minus 20 dB discrete reflectance. This is something, again, that is not validated at the component level in the field if you're doing light source power meter testing, Tier 1 testing. And again, this is the advantage of pre-terminated systems, because if you're using a pre-terminated system, that return loss is validated in the factory. So going over to the cabling standard, everybody is familiar probably with 568C.1. This is a snippet out of the standard, copied directly from the standard, and just breaking apart the cable channel in terms of permanent link, contributions of fiber in terms of attenuation, and contributions of splice and connector in terms of insertion loss. So there you can see that the link attenuation in terms of a simple equation is the cable attenuation plus the connector insertion loss plus the splice insertion loss. So most enterprise backbones, and I'll show you a scenario in a minute, typically comprise of a permanent link between two panels, say a TR and an equipment room, a closet and an equipment room, with fiber jumpers on either end. So what you've got there is you've got two connectors. And again, if this is a 10 gig link, the expectation is that in those two mated pairs of connectors, each of those connectors shall display no more than 0.75 dB of insertion loss. So here I have, and this is a bit of an eye diagram, but I hope you get the picture here. Here I have a typical enterprise backbone scenario, and I've colored the fiber as orange and the copper horizontal. So this is a star network with a TR, a telecom room, and an equipment room that would have maybe core level switching and workgroup switching in the TRs going out to workgroup outlets through a copper horizontal. So you can see the link that we're talking about here would be between the fiber patch panels in the equipment room and the fiber patch panels in the multiple telecom rooms. And I've said floors here, but these could be multiple telecom rooms spread about either a factory or an office space. So this is a scenario we'll talk to. Two mated pairs of connectors, no cross connect. We've got a mated pair of connectors in the fiber connectors in the ER. We've got a mated pair of connectors in the TR. So going back to the cabling standard, and I've highlighted this here in red, the cabling standard in terms of 568, the expectation would be that, and I've drawn out a backbone here of 200 meters just as an example. The expectation would be that I would have two connectors at 0.75 dB each max, and for 200 meters of fiber at 3.5 dB per kilometer max, I would have, based on the cabling standards, I would have no more than 2.2 dB. So if I did a Tier 1 test of that link, the max that I could accept would be 2.2 dB. To the right and left of that number, I have 1.4 and 3.9. So those two numbers, if I look at those, 1.4 would be based on, let's say, manufacturer's expectations on connectivity. If I had, let's say, a 0.35 dB LC connector, mated pair max, with the same amount of fiber attenuation, my budget would be 1.4. And there are customers out there that we come across that hold us to manufacturer specs. On the other side of the spectrum is what the application budget can stand. So this is a bit higher than the cabling standard, and it represents a worst case from the IEEE model itself. So it's a 200-meter channel, and again, that model is based on a 300-meter channel. So there's some give back of attenuation because it's a shorter channel. It's not a 300-meter channel. So there's some of the attenuation given back there that we can use. And there's also some of that ISI, that inter-symbol interference, the power penalties associated with, say, modal dispersion of the fiber that can be given back. So typically people set their power meters for the middle one. I'm going to talk a little bit about that in terms of installation, fiber termination. There are different ways of building these enterprise links. There are two main arms here. I've kind of diagrammed that out. We've got what I'm calling historical methods, and I've got plug-and-play methods. These are not mutually exclusive. I could have data center installations, say, with pigtail and splice. I could have enterprise installations, say, with plug-and-play. But mainly enterprise would be the historical methods of field polish connectors, mechanical cam and crimp connectors, pigtail fusion splice. Data center, we won't talk too much about that, but today's data center is typically built around MPO plug-and-play. The one I really want to focus on for this talk is a mechanical cam and crimp. And this happens to be Panduit's version of that connector. This is an LC connector. The one thing that's unique about this connector is that it is a two-cam system. So you have a cam, it's a fiber stub, pre-terminated at the tip. You mount the field fiber. It abuts the fiber pigtail in a cam area in that V-groove plank that you can see, and you make a field splice with the connector. What's different about this connector is that it is a two-cam system. I cam on the fiber, and I cam on the buffer, so in one action. So this connector is a reterminable connector. By uncamming the connector, I can release both the fiber and the buffer. So this is interesting, and you'll see further on why this is important, reterminability, because there are link commissioning issues. If I only do Tier 1 testing, and going back to that 568 equation that was a couple slides back, you have, with power testing, Tier 1 testing, light source power meter, you have the contributions of the individual mated pairs of connectors on either end, plus the fiber attenuation. So you're measuring overall power. you can't point to a single component, the fiber as a component, either of the connectors as a component, and say the loss is coming from there because you're measuring overall power. So you're trying to satisfy the budget. So you can't guarantee an individual connector unless you do Tier 2 testing. And again, that's important in the context of 10 gig because there is an expectation on both return loss on a component basis and insertion loss on a component basis. I'll just show you a scenario where that I could pass a link. I've done my permanent link test here, and my standards-based loss budget from the previous slides is 2.2. And let's see, I've just put a scenario here, 2.17 dB, and that's not quite success with respect to a 10 gig link because now I could have, and this is just an example, I could have a really smoking hot connector on one end, 0.05 dB. I've got average attenuation in the link, and the contribution there is 0.52 dB. But I have 1.6 dB on the other end. I've still passed the link, but I haven't passed the component expectation. So this is a concern when you're talking about higher speed links where I have to have a guarantee of component insertion loss. One of the issues when we're commissioning links really is, as a contractor, if I have a connector system in my hands, if I take 100 connectors and I terminate them in succession, how many of those can I get to pass in first pass? What is the yield? So we state that as a percentage. So if I had 95% on an individual single simplex LC connector, let's say, if I pass 95 out of 100 of those connectors without retermination, I get 95% probability of passing. So the fact that there are 4 connectors in the link, and you saw the previous slides, it's a duplex link. There's a connector mated pair on either end. So I've got 4 connectors. There are really 16 possible combinations of failure or passing. I could have obviously one way of passing the link, which would be all 4 connectors pass. I could have 1 failure in any of 4 locations. I could have 2 failures in any of 6 locations. I could have 3 failures in any of 4 locations, and so on. So that first pass yield is affected by how good the connector system is, what the expectations are on the channel, if they're really tight, if people are holding us to their manufacturer specs, what the test methodology is, how good the test set is, how good the contractor is at terminating the connector system. So what we've done, and this is the wrap up of the presentation, and the core of the presentation is we've built a model. It's a probabilistic model that takes in all of those combinations of failure and looks at component cost, the first pass yield that we talked about on an individual connector basis, the labor cost for installation, initial installation, remediation if needed, and testing. And it puts out some interesting outputs. It puts out total scrap and total scrap and error. So what I'm going to talk about that in a minute. But what that means is if I have, let's say, a non-reterminable connector system, like a field polish system, and I cut off the wrong connector to reterminate. So it was really a good connector, but I cut it off. This is an honest mistake that happens all the time, particularly when the first pass yield is low and you're only doing Tier 1 testing because you can't determine where the source of the failure is. So again, this is a model that we've built, and I'm going to go through in the following slides focusing on those outputs, the installed cost. And what I hope to show is that there is really a great value and a simple payback in doing Tier 2 testing and finding out immediately which connector end failed. And again, a bit of an eye diagram here, but the crux of this is first pass yield. So what I'm calling the scrap and error is an outcome of a a mistake that's made with respect to cutting off the wrong connector. If I'm only doing tier 1 testing, I don't know necessarily, unless it's a catastrophic failure and let's say I VFL it and I see that light is spilling out of the connector. Typically, if I have marginal failures, it's very difficult to determine, if I don't have tier 2 testing, which end failed. So as a function of first pass yield, how good the termination is, I create scrap and error. So as my scrap and error, as my first pass yield goes down, my scrap and error goes up, kind of exponentially. So the example that I show here is at 85% first pass yield, I'm creating 8% scrap and error. So that means not only do I have 15% true scrap, I have an additional incremental 8% scrap and error. And that's a function of, again, as stated in the bottom here, not doing tier 2 testing, not identifying which is the true failed end in the link. And a lot of times if you're building closets and equipment rooms, and in particular, if you're doing assembly line, which we don't recommend, assembly line termination, a lot of the times all the closet connectors are built and you're ending up with a lot of cable coming back into the ER, and you're ending up with the toolkit back in the ER, and you're terminating there. And a lot of times the decision to remediate which end comes down to, well, where's the connector toolkit? I'm going to try this end. And it's not a systematic approach with tier 2 testing where I'm immediately identifying which end has failed and immediately remediating that. Again, the value of tier 2 testing. Another output of the cost model is, as a function of that first pass yield, the fact that I have to re-terminate and I have to retest, what does that cost? So here is a graph of what we estimate as installer first pass yield, kind of a range of 80% to 95%, 97.5%. We see that as a typical range of first pass yield on field connectors. You can see that there's an incremental cost per link by not using a reterminable connector. The value in a reterminable connector is I can take it off and I can try it again and put it back on, and I'm not throwing away a connector. So there is value in that. There's value in the labor saving and obviously in the component saving. So I've used that 85% data point again in first pass yield. And what you can see here is the first pass yield at 85%, there's a 16% cost increase per link in not using a reterminable connector system. And again, tier 2 testing reduces the labor associated with these efforts and minimizes cost. I hope this is showing up on the screen, but this is a little bit difficult to understand, but I've got a labor rate and first pass yield model. So as a function of the labor rate and as a function of first pass yield, I can start to estimate, if I do tier 2 testing, what can I save, or what am I leaving on the table conversely as lost revenue as a function of first pass yield and labor rate. So you can see here there are bands of loss, or potentially how much I could gain back if I do tier 2 testing. So the least loss is obviously as my labor rate is very low and my yield is very high. Conversely, the greatest loss is where I have a high labor rate and a very poor first pass yield. So I've kind of split the difference here, and I said, okay, at $80 an hour with an 85% labor rate for a 250 port job as an output from the cost model, with no tier 2 testing, I'm suffering a $3,000 loss. Now, if I look at that $3,000 and I look at something, let's say like the Fluke Quick Map, I could probably easily buy a couple of those for that money that I'm leaving on the table. Last slide. Again, just reinforcing the value of reterminable testing. The value is in, this is the ultimate combination to have a reterminable connector that minimizes wastage, not having to cut off connectors, And again, Tier 2 testing, which goes immediately to the source of the error and precludes these connectors that are cut off in error, so minimizing expense. And what I state here is that most connector systems are not returnable after initial installation, and engaging the light by visual or automated means, prior to doing the link test, which is the acid test, that doesn't guarantee that the link will pass. So such gauging methods produce both false positives and false negatives. And again, the acid test for component performance on an individual basis, return loss and insertion loss, is Tier 2 testing. And that's the end of my presentation, and I'm going to turn it over to Patrick to introduce Harley. Patrick?
Robert, thank you very much for that information. I'll just quickly remind the members of our audience that you have the capability to submit questions at any time. If you have questions for Robert, please feel free to submit them now or throughout the remainder of the seminar. Also, any questions intended for Harley can be submitted at any time during Harley Lang's presentation, which will begin now. Harley will deliver his portion of today's seminar on minimizing deployment costs of enterprise fiber. Harley, whenever you're ready. Thank you.
Thanks, Patrick. Let me move to the next slide here. So I'm going to talk a little bit about field testing, fiber specifically, follow up a little bit from Robert's presentation about reterminable connectors and sort of the marriage between fault troubleshooters and Tier 2 testers and reterminable fiber connectors. But first I'd like to start out by just talking about fiber testing and how that applies to general situations, not just when using reterminable connectors. Just to start out, I want to make the point that all the good reasons for testing fiber optic cabling infrastructure apply. I won't reiterate all the benefits of testing and certifying cable. We'll assume that our audience understands the benefits of knowing that cabling installation was done properly and that the components and the as well as the installed cabling system must perform well in comparison with a standard in order to be able to not only get a warranty but be able to ensure the performance of the cabling system and the applications that are run over it long term. What we'll focus more on once I give you a review is how field testing in some cases can be a special contributor to increasing connector yield and lower cost. I think this is kind of the interesting angle of our presentation that Robert has alluded to already. So let's start out with a review of fiber optic field testing, best practices, tools, and methods. I'm going to hit the high points here. The most basic tool that most technicians are familiar with is a visual fault locator, or VFL. In the old days, testing continuity was probably the most important thing for technicians, considering that our loss budgets were so high. The things have changed, though, and actually measuring the loss and certifying the loss, comparing it to a standard, is important. The limitation of a visual fault locator, like this slide indicates, is that it can determine continuity and help solve some polarity issues, but it cannot determine the difference in power that you might be able to that you would be able to detect with a power meter light source. So it cannot measure the loss. It just is a simple check of continuity, and sometimes can be used for polarity. But certification testing is, it does a lot more. There are two parts of certification testing. Basically, in a nutshell, we're comparing, when we do a certification, a Tier 1 certification, which I'll explain over the next few slides, compares the loss that comes from the events and all the cabling within a channel or a link to an industry standard. And then we have our Tier 2 test, which compares the loss and reflectance of events of those components or instances specifically, and compare those to either an industry standard or contractual obligations. But I want to remind the audience that the first part of all testing is cleaning. Without clean connectors, testing can be less productive than you'd like it to be, and accuracy can be compromised. So that's why I have cleaning here on the very first slide of certification. But talking a little bit further about Tier 1 certification, in this case we're using, the diagram is using a dual fiber optical loss test set. But the first step here, and in all certification, is setting a reference. There can be a lot of confusion about setting a reference. The important thing is that what we're doing is we're just determining the power output of the optical source, so that we can later on, once we install a fiber to test or a fiber under test, we're able to know what our source output is and compare the difference, and that's how we get our loss. There are a couple different methods for testing or for setting a reference. The preferred method is the one-jumper method. It gives us the best reference of our source power and has the lowest uncertainty once we test our fiber cabling. One other thing just to point out is that it's important to use reference grade test reference cords. And this is actually pretty easy to verify for. There's a lot of cords out there, and with varying levels of quality. A patch cord, a low-cost patch cord that could be maybe used in a cabling system is not usually adequate for doing certification work. It's not adequate as a test reference cord. And so if you're not using a test reference cord that came with a tester, you can test it pretty easily. Once you set a reference, you can insert it in as the diagram here on the screen shows. And we also have many knowledge-based articles on the Fluke Networks website that show you how to test cords. But you can actually test the cords that you have to make sure that even if they're good quality test reference cords, that they haven't degraded over time, to make sure that you have good test reference cords. And having good cords also reduces some concerns that some people have about setting a reference and using where you have to use a known good cord. So those cords can be verified in the field. And really the final step of setting up to test the cabling using the Tier 1 certification, or loss certification as some people call it, is selecting the correct test limit. This is pretty easy to do depending on the test equipment that you're using. You can choose the test limits from a menu that's loaded into the OLTS, And in this case that we're showing on the screen, the tester will prompt you for the number of adapters because we're using a TIA limit, so it's actually pretty easy to set that up. Again, cleanliness is paramount. Another thing just to point out that many of the audience has already heard is that dust caps is kind of a misnomer. Really, they're protective caps to protect the ferrules of your test cords and the end of your fiber cooling. They should always be clean. In fact, dust caps can actually add contaminants to the end faces of the fiber. So always use the caps to protect the end faces, but always clean after they've been removed before they go into a piece of test gear or into a connector adapter. The limitation of Tier 1 certification is that it gives an end-to-end loss measurement that's highly accurate, but it can't determine the performance of individual connectors. Robert indicated this earlier. So I have my different connectors, usually at a bulkhead, sometimes a cross-connect, and really with Tier 1, all I get is my end-to-end loss. I'm not able to really see what the loss of the individual connectors might be, so I could have a good one that's compensating for a bad one, and I really don't know. I passed my limit. So that's where Tier 2 certification and troubleshooting comes into play. So that's what I'll talk about next. Tier 2 certification typically involves the use of a very sophisticated piece of test equipment called an OTDR, or optical time domain reflectometer. An OTDR can measure the performance of all the events in a fiber channel, and this is connectors, splices, tight bends. It can see all those things. Like I said earlier, in the last few years we've seen a pretty nice connection between Tier 2 testing and reterminable mechanical style connectors. But I think what's even a better marriage probably is with a simpler tool like Robert had indicated earlier, the Fiber Quick Map, that's simpler than an OTDR, but it's able to measure individual events in a fiber link. So in comparison with an OTDR, it's easier to use, easier to learn, lower cost, and works as a good tester in the field to put in the hands of a technician who's actually doing the termination. So the question is, how is it used? How does it compare with other testing that we've seen in the field? It's actually quite simple. You use a launch cord, just like what you would use with an OTDR. You can set test limits, press test, and you can use those limits to determine the performance of that first connector. So we're able to tell whether that connector termination is adequate or not, and specifically be able to tell which connector needs to be re-terminated. So there's no guesswork involved with this tool. And you can also do that in the reverse direction to test the connector on the other end. So you basically repeat the process and test from the other end to check the connector on the other end of the cable. So a very, very simple way to determine the performance of those two end connectors on a link. Just to kind of reiterate, there are different kind of failure indications on the Fiber Quick Map in comparison with some other testers that you might have used, but pretty easy to read. In some cases, in many cases, the remediation should be to clean the end faces. So I want to reiterate, and I think Robert would back me up on this, that before a connector is cut off or removed and re-terminated, in the case of a reterminable connector, it's important to first go through a cleaning cycle because it should be a lot easier to clean the end face than to remove the connector and re-terminate it. So first, always re-clean the fiber end face and retest. If it fails, the retest. Then go through the re-termination procedures for that connector that failed. So then, just in summary, there are some best practices that we need to follow. What we focused on today has to do with saving costs. I think that's probably one of the most important best practices, keeping our costs down. Re-terminal connectors can be one of the ways to do that, especially when coupled together with a tester that can take some of the guesswork out of which connector should be re-terminated. Again, though, certification testing is critical. So the cabling needs to be certified for Tier 1 to make sure that the loss is in compliance with the standard. And then we can use Tier 2 certification or the use of a fault troubleshooter like the Fiber Quick Map to reduce the scrap and make sure that the component compliance is good. So when you think about troubleshooting, and which is kind of an offshoot of Tier 2 certification, and using a product like the Fiber Quick Map can reduce the rework, the guesswork, and ultimately, when we're doing a full certification and making sure that our cabling infrastructure meets the requirements of the standards or even exceeds, we can prevent link downtime and create happy customers, solid cabling network cabling systems. So with that, I would like to turn it back over to to Patrick.
Harley, thanks very much for that information. Thanks to the members of our audience for attending today, for participating, and I know a number of you sent in questions. Harley, again, thank you for that presentation. A number of questions did come in. I think we'll give Harley a breather for a few minutes while we turn some questions Robert's way. If we have Robert on the line, we do have a handful of questions lined up for you, and wondering if you can address some of them at this point. Robert, do we have you?
Sounds great.
Great, thank you. I've got 4 or 5 of these for you. I'll get as many of them off to you as I can, and then we'll turn to Harley. One question that came in: how many times can a person re-terminate a mechanical cam-style connector, which you described in your presentation? And Robert, sorry, before I could jump in, please feel free, if there's as I ask these questions, if there's a particular slide from your presentation that applies, please feel free to call it up. In fact, I think I'm going to try to do that now with that one. I believe that this question relates to this type of connector that you displayed. How many times can you re-terminate a mechanical cam-style connector?
Well, if the cam connector was terminated in a clean room, the number would be very high, but we know that these installations happen, where drywall is being cut and carpentry done. So we typically, for this connector here, we typically say 3 terminations. 3 re-terminations is a good number, and that's a function of 2 things: pushing debris back into the connector, into the area, the clamp area, and pulling gel out. So those two things over time, minimize the effectiveness of the connector.
Thanks, Robert. Another one for you asks, from the standpoint of an installation contractor conducting certification, says my customers only demand Tier 1 testing done with a light source power meter. What is the risk of performing Tier 1 only and not performing Tier 2 testing?
Well, the risk is probably, it's non-existent for 1 gig networks that don't have these requirements on return loss at the component level and insertion loss at the component level. And these are odd cases where you would have a connector that would be misbehaving in a link. The one that I showed in the example would have an extremely low connector loss, and the one would be extremely high. It's really the higher speed links. I mean, if you're doing fiber channel 8 gig and above, if you're doing 10 gig Ethernet and above, these are the requirements at the component level that would maintain application standard compliance.
Robert, thanks. Shooting another one your way. Question asks, what if I pre-test my connector, meaning a visual inspection of scattered light out of the connector or inferred loss? What if that pre-test of the connector is done prior to the final connector installation? Doesn't taking such a step kill the scrap and error issue that you described in your presentation?
Yeah, I think it does somewhat, but you have to look at it like the ultimate test, the acid test is, the link test. So even with that, you will get failures, things that look good visually or measured, pre-measured as visually good can fail in the link, and conversely, ones that look bad could be actually good. So the best practice is, rely on the link test as the acid test.
Got it. Thank you. Robert, I'm going to pull up another one of your slides as I asked this question. I think the slide that's now displayed, it might have been what prompted, or maybe a slide or two that followed, it might have been what prompted this question from the audience. Asks, how does one determine the ISI feedback or allowed channel insertion loss for a given length channel? Is there an application, a standards-based formula that is readily available to use for that purpose?
Yeah, unfortunately, contractors only have 568 or international standards in hands for cabling, and these application standards are not exactly straightforward in terms of guidance on channel budget. There is leeway beyond this 2.6 that's stated here as a channel insertion loss, and some of the give back from ISI. Manufacturers typically have calculators. We have a calculator. Applications engineers have calculators that can do this for customers and do these trade-offs. It's a dangerous thing, and you tread a thin line if you do this willy-nilly. So what I would recommend here is that you work with your manufacturer, your connectivity, your cabling manufacturer to work through these issues. If you're going beyond the standards, if you've got more connectors in the channel, if you're trying to push the length of the channel and so forth.
Thanks, Robert. I think we've got one more to send your way before we ask Harley a couple of questions. And that question for you, Robert, is why is it important to pass the component, to pass on a component level if your channel passes anyway? If the channel passes, doesn't that mean that the system works? And bottom line, that's what's important. And I know you've got a slide that kind of addressed that as well. Go ahead.
I think we kind of answered this in the first question. Again, it's adherence to the application standard, and it's maybe not so important for 1 gig links, but for higher speed links, the application guidance is to have both a guarantee on the individual component loss of no more than 0.75 dB per connector. The reason for that is buried in the esoterica of the IEEE model. What starts to happen is you start to blow up something called modal noise. I think that answers the question.
Robert, thanks very much for all that information. Very much appreciated. If we have Harley on the line, Harley, I think we've got the opportunity for a couple questions to send your way before we wrap up. Do we still have you?
Yep, I'm here.
Thanks, Harley. One question comes in concerning bend-insensitive fiber. Question asks, how does Fluke Networks account for bend-insensitive fiber? Person who submitted the question says, I understand that reference-grade cords were being built with bend-insensitive fibers, thus impacting the effectiveness of mandrels.
Mm-hmm. Yeah, let me, there was another question about mandrels. I think it was number 12, too.
Yes, the other one I was going to ask you, Harley, what's the purpose of mandrels and are they needed? Perhaps those two questions might be addressed in one shot.
Exactly. So I thought maybe what I'd do is first talk about, answer the one that asks what the purpose of mandrels are, and then talk about the sort of the nuance of bend-insensitive fiber and mandrels. So the purpose of using a mandrel when setting a reference is I'll kind of give the technical answer and then break it down. Purpose of using a mandrel is to remove what's called higher order modes of light that will disperse or absorb over once a test is underway. It turns out that in very short reference tests, you will get light in a multi-mode system. You'll get light that travels in the cladding or outer parts of the core of a fiber. So what you need to do is use this mandrel to strip those modes of light away, because they would have or will absorb or disappear as soon as you plug it into a fiber of normal length that you're going to test. The reason why you want to do this is because if you don't, you'll have false failures, which is a pretty silly thing to live with. The reason why that'll happen is because the reference value will show up as hotter than it actually is. So you want to use mandrels. It's really just for the referencing process. The second question about bend-insensitive multi-mode fiber is an interesting one. When you think about the use of a macro bend, which is basically what mandrel is doing to strip those higher order modes away, if you use a bend-insensitive multi-mode fiber, it won't strip those higher order modes away at the rate that was calculated when the diameter of mandrel was decided on. So the question is, what is Fluke? How does Fluke account for bend-insensitive fiber? Well, what we do is we use non-bend-insensitive fiber for our test reference cords. And so you can go ahead and use the mandrel that you've always used. And it'll strip away the higher order modes as was designed in the standards and with that diameter mandrel, because obviously there's a different diameter mandrel for both, for each 62.5 micron and 50 micron. There is some work underway with trying to figure out what diameter of a mandrel you would need for bend-insensitive multi-mode fiber in order to accomplish the same thing, but that's so far, to my knowledge, incomplete.
Harley, thanks very much, and we're pretty close to the top of the hour. I think the subject matter's been covered quite well. Questions that have come in have been largely answered. We very much appreciate every member of our audience participating today. The questions that were submitted, remind everybody that this seminar will be available on demand within 24 hours. So on behalf of Cabling Installation and Maintenance and its parent company, Penwell Corporation, I thank today's presenters, Robert Reed and Harley Lang, for the presentation that you've just seen. Reminder to everybody in our audience that very shortly you will receive an email that will include a link to your attendance certificate should you wish to use that. Please remain on the line as we disconnect here. You will receive a pop-up window indicating that you've made it all the way through, and your email will follow shortly thereafter. I thank everybody once again for joining us today and hope that we're able to meet some of your information needs with today's webcast and that you'll join us for webcasts again in the future. Thanks again to everybody, and have a good day.